Hello everyone, Namaskaram, Namaste everyone. Namaste everyone. Okay, in this video we're going to discuss matrices and determinants for GATE 2027. Okay, did you know that engineering mathematics carries 15 marks in almost every GATE paper? Okay, that is 15 free marks if you know the right strategy. Welcome to lecture 1 of the complete GATE mathematics series for all branches. Okay, I am going to cover all the GATE syllabus. Okay, for all the branches. This is the lecture 1. In this lecture 1 we are going to discuss some basics and matrices and some special matrices and like determinants and rank, system of equations, trace. Okay, all these topics we are going to cover in this live session. I am Akshay, and in this series we won't just learn math, we will learn how to score in math. Okay, today we start with the backbone of linear algebra, matrices and determinants. Okay, whether you are CS, ME or EE or ECE, this topic is non-negotiable. Okay, this is a very easy topic and very important also. Okay, like in this session we're going to cover all these topics, and next session I'm going to cover eigenvalues and some other topics. Okay, let's start with some basics. Okay, in this topic like total weightage. Okay, total weightage of like mathematics. Okay, in GATE mathematics, that is around 13 to 15 marks. Okay, complete syllabus weightage around 13 to 15 marks. See, even GATE, in GATE exam 1 mark also very important. Okay, for getting rank is very important. Okay, for rank 1 mark also very important, be careful, and easily we get 15 marks, 13 to 15 marks here in GATE mathematics. Okay, and let's discuss with some basic definitions. Okay, we know that matrix is a rectangular array of numbers arranged in rows and columns. Okay, actually we denote matrix with like these symbols, or sometimes we denote like this also, the both are same. Okay, if any numbers we take horizontally, such horizontal arrangements are called as rows. Okay, if you arrange the numbers in vertically, such type of vertical arrangements are called as columns. Okay, is it clear? And order, or it is also called as dimension. Okay, in matrix language called as order. Okay, if it is come to linear transformation, we call this dimension. Okay, a matrix has m rows and n columns. Okay, its order is m by n. We read as like it is not into. Okay, it is not a multiplication symbol. We read like m by n matrix. Okay, and the element, the entry in the ith row and jth column is denoted as aij. Okay, we denote matrices in generally aij. Okay, m by n like this. Okay, here aij indicates element of the matrix, element. Okay, and here m we know that number of rows, here n we know that number of columns, and here in aij, I indicates the, see, ij indicates the position of that that element. Okay, I indicates the row. Okay, ith row position, ith row. J indicates jth column. Okay, for example, if you consider a matrix, like I will denote the matrix like this: a11, a12, a21, a22, here this is the matrix. If I will consider, okay, here how many rows, if you see, if you count horizontally, okay, how many lines we can possibly draw like this horizontal? 2, right? 2, that means 2 rows. Okay, similarly vertically how many? 2, that means 2 by 2 matrix, 2 rows, 2 columns. See, and a11, a12, a21, a22 called as elements of the matrices. Okay, and here a11, see here a11 indicates that this element present in first row and first column. Okay, this element located at first row and first column. Similarly, if a21 is there, this element is located at second row and first column. Okay, this is the meaning of 21. Okay, a21. Okay, that for that element, the location of that element indicates by this ij. Okay, just remember this basic okay things. And in a square matrix, number of rows and number of columns are equal. Okay, if you want to say the matrix is square matrix, then number of rows and number of columns should be equal. Then only we say that the matrix is square matrix. Otherwise the matrix is not square matrix. We call such type of matrix, if M is equal to N, square matrix. Okay, if M is not equal to N, such type of matrix we call as rectangular matrix. Rectangular matrix. Okay, like for example, if you consider order 1 by 2, okay, this is a rectangular matrix. Number of rows and number of columns are not equal. Such type of matrices are called as rectangular matrix. If number of rows and number of columns are equal, such type of matrix are called as square matrices. Okay, then we discuss about operation on matrices. Okay, first one is addition and subtraction. Okay, there are two matrices. If you consider Aij with order m by n, okay, B matrix Bij, it is also same m by n. So if you want to add two matrices, can be added as subtracted only if they have same order. This is very very important. Okay, we can add any two matrices, or we can subtract any two matrices only possible, okay, if the order is same. Okay, if order is same, then only it is possible. Otherwise addition and subtraction is not possible. Okay, if it is both are orders are same, then a plus b, that is equal to, we add corresponding elements. Okay, the same position elements we add aij plus bij. Okay, in generally we can consider one example. If you consider this example, okay, we get 6. Similarly 2 plus 6 we get 8, 3 plus 7 we get 10, 4 plus 8 we get 12, like that. Okay, this is the addition of matrices. Okay, then we discuss scalar multiplication. Okay, what is scalar multiplication? Multiplying a matrix by a constant number. Okay, a constant number means it is maybe any real number except 0. Okay, except 0, you can multiply it any real number. Okay, k involves multiplying every element in the matrix by k. Okay, like this. Okay, for example, here a matrix is given like this: 1 3 6 2. For example, I want to find 2a. What is the value of 2a? Then 2 into what is a matrix? 1 3 6 2. Okay, 2 is a number. Okay, if it is a number, this number involves multiplying every element. Okay, see, this element should be multiplied with each element. Okay, then we get 2 into 1, 2 into 3, 2 into 6, 2 into 2, like this. Then we get 2, 6, 12 and 4. Okay, this is nothing but scalar multiplication. Okay, then matrix multiplication. See, scalar multiplication and matrix multiplication both are different. Scalar multiplication means we multiply any number with matrix. Okay, number, we multiplying number with matrix, that is nothing but scalar multiplication. Matrix multiplication means we multiply matrices. Okay, both are matrices only, we multiplying with matrices, then we call as matrix multiplication. Okay, if you want to multiply any two matrices, okay, then see, if two matrices A B can be multiplied only if number of columns in A equal to number of rows in B. Okay, two matrices are multiplication is possible only if number of columns in A equal to number of rows in B, then only matrix multiplication is possible. For example, A as m by n order, B as n by p order. Okay, I will write here, it is easy to, okay, like this, n by p. Okay, this order, if you want to multiply these two A B, then m by n, okay, n by p. Okay, this multiplication only possible when these two are equal. If these two are equal, okay, number of columns in A and number of rows in B, if these two are equal, then only matrix multiplication possible, and our resultant matrix AB, this order should be equal to m by p. Okay, will be m by p, we get like this. Okay, is it clear? Okay, we will consider one example. See, I will explain with simple example. If I will consider A matrix 1 6 3 2, B matrix, okay, 3 1 minus 1 2. For example, if I will consider these two matrices, okay, how to multiply this? AB is equal to 1 6 3 2, okay, 3 1 minus 1 2. See, first you should multiply first row with first column, remember. Okay, first row first column elements. Okay, write down 1 6 plus 3 minus 1, you can write down like this. Okay, this is the shortcut trick, you can remember. Okay, first write down first row first column elements like this, 1 6 and 3 minus 1, and then multiply 1 into 3, 1 into 3 we get 3. Okay, plus symbol is there, plus, and 6 into minus 1 we get minus 6. Okay, if you simplify this, what is the answer? We get 3 plus into minus 6, nothing but minus 3 we get. Then this position first element we get minus 3. Similarly, first row second column element, first row for second column element, 1 6 1 2. Okay, then multiply 1 into 1 1 plus 6 into 2 12, that is equal to 13. Okay, next, first row, is there any other columns here? No, then you end here, then come to second row again. Okay, come to second row, multiply second row with first column. Okay, I will erase this one, 1 minute. See, okay, then multiply second row and first column elements, plus 3 comma minus 1, multiply 3 into 3 3 is 9, plus 2 into minus 1 minus 2, simplify 9 minus 2 we get 7. Okay, we write down here 7. Next, second row second column, 3 2 plus 1 2. Okay, 3 into 1 3 plus 2 into 2 4, we get 7. Okay, next, second row, is there any other columns here? Second row, is there any other columns? No. Then close this one, brackets. Okay, like this you should multiply two matrices. Okay, any two matrices you can multiply like this. Okay, next, you always remember these points, very important. Okay, the order matrix. Okay, see, in multiplication order matters. Okay, if order, if order is interchanged, okay, then AB is not necessarily equal to BA. You should remember this one. Okay, order matters in multiplication. AB is not necessarily, in general, AB is not equal to BA. You should remember this one, very important. Okay, and zero product property. If AB is equal to 0, okay, it does not imply that A is equal to 0 or B is equal to 0. It may be any non-zero matrices also. For example, see, I can give example 0 1 0, sorry, 0 1 1 0 and 1 0 0 1. Multiply this, what is the answer we get? 0 0 0. See, this A, this is B, they both are non-zero matrices. Okay, what is zero matrix? Zero matrix means all the elements should be 0, then only we say that that type of matrix is zero matrix. But these both are non-zero matrices, but if you multiply these two we get zero matrix. Okay, that means, okay, there is no necessarily equal, A is equal to 0 or B is equal to 0. Okay, this is not necessary, you should remember. And cancellation law, if AB is equal to AC, you cannot simply cancel A to say B is equal to C. We cannot cancel like A cancel like this. Okay, we cannot cancel like this. Okay, if it is in numbers like 2x equal to 4y something, we can cancel. Okay, it is both the numbers. If the numbers, we can cancel like this, and x equal to y, we can write like this. But if A B C D are the matrices, if these are the matrices, we cannot cancel simply. Okay, you should remember this one, very important. And special type of matrices, zero matrix, all the elements are 0, that means 0 0 0 0 0. Okay, zero matrix is depends on order. It may be square matrix or rectangular matrix also. Okay, depends on situation. Okay, we consider zero matrix, it may be square or rectangular. Zero matrix means all the elements should be zeros. Such type of matrix is zero matrix. What is identity matrix? Identity matrix means, for example, if you consider 3 by 3 matrix, okay, all the diagonals should be, see, these are the positions. See, in diagonal matrix, all the diagonals should be, see, in diagonal matrix, all the diagonals may be any real number, it may be any real number. Okay, but if you want to say the matrix diagonal matrix, non-diagonal position should be 0, except non-diagonals, sorry, except diagonals, remaining all the position elements should be 0. Okay, such type of matrix are diagonal matrix. See, diagonal matrix is a square matrix, you should remember, square matrix. Okay, identity matrix also a square matrix. Okay, it is a diagonal. What is identity matrix? In identity matrix, it is also a square matrix and a diagonal matrix, but the speciality is all the diagonals should be 1. Okay, all the diagonals in a square matrix with ones on the main diagonal and zeros elsewhere. Okay, in remaining position all zeros. Such type of matrix is identity matrix. If you consider 2 by 2 matrix, it is 1 0 0 1 we write. If you consider 3 by 3, 1 0 0 0 1 0 0 0 1. Okay, these are diagonals. Okay, diagonal elements, except these diagonals remaining should be zeros and all the diagonals should be equal to 1. Such type of matrix are identity matrix. And diagonal matrix means except diagonal elements, remaining positions should be zeros, that is diagonal matrix. Okay, and there is a one more matrix, scalar matrix. Scalar matrix nothing but the matrix, see, it is a diagonal matrix only, but in scalar matrix all the diagonals elements should be equal. Okay, all the diagonals elements should be equal. Such type of matrix are scalar matrix. Okay, next, transpose of the matrix means interchanging rows and columns. Such type of matrix are transpose of a matrix. Okay, for example, a matrix 1 6 3 2 4 9. Okay, what is the transpose of this matrix? Interchange the rows and columns. I will write first column as first row 1 3 4, second column as second row 6 to 9. Okay, interchanging rows and columns, we get a transpose of the matrix. Okay, this is very important, you should remember this one. Okay, if suppose A is m by n order, if you take transpose, okay, order will change. Okay, n by m. Okay, you should remember, and some properties you should remember. Okay, A transpose whole transpose is equal to A, and second one AB whole transpose is equal to, you should take ulta, okay, reverse order. Okay, B transpose into A transpose, this is very important property. And third one A inverse whole transpose, that is also equal to A transpose whole inverse. Okay, this is also very important property, you should remember. Okay, these properties are important. And one more property, A plus B whole transpose is equal to A transpose plus B transpose. A minus B whole transpose is equal to A transpose minus B transpose. Okay, these properties you should be know. Okay, per transpose of the matrix. And symmetric matrix means A is equal to A transpose. Okay, and you should remember symmetric across the main diagonal. Okay, and skew-symmetric matrix, A is equal to minus A transpose, diagonal element must be 0. Okay, you should remember this one. See, in symmetric matrix, A is equal to A transpose. Okay, for example, if I will consider one example, see, for example, 3 by 3 matrix, if I will consider, okay, these are the positions. See, diagonals element should be any real number. If you want to say symmetric matrix, diagonal should be any real number. Diagonal should be any real number, A, B, C. Okay, just take mirror image of this diagonal. Whatever the element present here, that same element should be present here. Okay, and whatever the element present here, the same element should be present here. Okay, whatever the element present here, the same element should be present here. Okay, this is nothing but symmetric matrix. Okay, you should remember this. And come to skew-symmetric matrix. In skew-symmetric matrix, all the diagonal elements must be 0. This is the first condition. For example, 3 by 3 matrix, if you consider 3 by 3 matrix, okay, if you want to say the matrix is skew-symmetric matrix, all the diagonals should be 0. First condition, diagonals must be 0. Okay, then whatever the element you take in this position, if you take symmetric like this, what are the element you take this position, the same, if it is plus A, the same element but opposite sign. Okay, if it is minus C, for example minus B, here we take plus B. If it is C, we take here minus C, like this. It is nothing but skew-symmetric matrices. Okay, symmetric matrix, skew-symmetric. Orthogonal means A into A transpose is equal to identity, and determinant is always plus or minus 1. Okay, we will prove the determinants later. Okay, I will explain how to take determinants of this. Okay, it is very easy, I will explain this one. And idempotent is equal to A square is equal to A. Such type of matrix are idempotent matrix. And involuntary, if A square is equal to identity, then such type of matrices are called as involutory matrices. These are the special matrices you should remember. And nilpotent matrix is there. Okay, nilpotent matrix, that is also important. Nilpotent matrix means a raised to power of k is equal to 0. K is least power. Okay, for example, if a is some matrix is given, okay, non-zero matrix. Okay, if you take a square, okay, again we get non-zero matrix. Okay, non-zero matrix. If you take a cube is equal to a cube, then you get 0 matrix here. For example, you get 0 matrix, then okay, it is called as nilpotent matrix. Okay, and okay, then a is called as nilpotent. Okay, you should remember this. Okay, next, determinant and inverse. Okay, determinant is only applicable to square matrices. Determinant is only applicable to square matrices. Determinant we denote like this, det of a, or sometimes we denote it like this. Okay, scalar value. What is determinant? Determinant is a scalar value. Scalar value means constant value. Okay, it may be any real number calculated from a square matrix. Okay, you always remember determinant is just a number. Okay, determinant is just a number. Okay, it is a scalar value calculated from a square matrix. Okay, remember this one. If it is a matrix, 2 by 2 matrix is given, determinant of a is just multiply these two elements, we get AD, take minus, then multiply these two elements, we get BC. Okay, this is for 2 by 2 matrix. If it is 3 by 3 matrix are given, how to find determinant? A, B, C, D, E, F, G, H, I. Okay, these are the elements. Okay, how to find determinant of 3 by 3 matrix? First consider this element. Okay, see, always you remember this order, plus, minus, plus. Okay, if you consider this element, okay, now you should eliminate that, okay, that row and that column. Okay, whatever the element present, you should take here E, F, H, I. Then with symbol minus, then consider this element B, then you delete that column and row. Okay, whatever the element present, you should take D, F, G, I. Then plus symbol, plus C. Okay, then delete okay, delete that column and row, whatever the elements are there, just write down here. Okay, then you know this is a 2 by 2 determinant, and simplify, you get the answer for 3 by 3 matrix. Okay, and if determinant of a is equal to 0, if determinant of a is equal to 0, such type of matrix are called as singular matrix. Singular matrix, that means non-invertible. Non-invertible means inverse does not exist. Inverse of the matrix does not exist. Okay, if determinant of a is not equal to 0, such type of matrix are called as non-singular matrix. Non-singular matrix, that means invertible matrix. If determinant of a is not equal to 0 means such type of matrices are invertible matrix. Invertible matrix means inverse exist. Inverse of the matrix will exist. Okay, you should remember this one. Okay, these are the some important points related to determinants. Okay, later we will discuss properties related to determinants. First we will discuss inverse also. What is inverse? A inverse, we denote with the symbol like this, A inverse. Okay, a power of minus 1. If you take like this, this is nothing but inverse of the matrix. Okay, if A into A inverse, that is equal to A. If A inverse is, okay, inverse of A, then product of those equal to, we get identity. Okay, for example, if suppose any matrix is given like this, A B is equal to identity, this nothing but, okay, what is the meaning of this? AB is equal to identity means AB are both are matrices, okay, square matrices, okay. Inverse matrices exist only for square matrices, okay, like determinants, okay. Determinants and inverse only exist for square matrices only, you should remember, okay. AB are square matrices. If the condition is given like this, AB is equal to identity, the meaning of this, A is inverse of B, or B is inverse of A. It can be written like this also, A is equal to B inverse, or B is equal to A inverse, okay. You should remember this one. This is nothing but inverse of the matrix, okay. There is a formula to calculate inverse of the matrices, okay. General formula, A inverse is equal to 1 by determinant of A into adjoint of A, okay. Determinant should be not equal to 0, then only inverse will exist, okay. Okay, first we should calculate adjoint of A. Adjoint of A is equal to, for 2 by 2 matrix, say I will give a shortcut trick to find adjoint of A. For 2 by 2 matrix, this is the, for example, A B C D, it is a 2 by 2 matrix, okay. This is the matrix A given, then adjoint of A is equal to, just interchange the diagonal elements and take opposite sign to non-diagonal elements, okay. If it is plus B, we get minus B, if plus C, we get minus C, like this, okay. This is the adjoint of A, okay. This is for 2 by 2 matrix. For example, if it is 3 by 3 matrix, say I will give shortcut trick for 3 by 3 matrix, you should remember. For example, if I will consider a matrix 1 0 minus 1 2 3 1 minus 1 0 3, for example, if I will consider a matrix like this, okay. How to find A inverse? Okay, to find A inverse, I should find adjoint of A first, okay. I need to find adjoint of A first, okay. For finding adjoint of A, I will give a shortcut trick, you should remember, okay. First always start with middle element. This trick is only applicable for 3 by 3 matrix, okay. Remember, see, always you should start with middle element, okay. Write down 3, then that below element, okay, 0, write down here, then that above element, that is 0, then again same element 3, okay. Then again start here, again select this one, middle element 1, and that below element, same process again 3, again that above element minus 1, and the same element 1, okay. Again the same process you repeat here, middle element 2, okay, that below element, okay, minus 1, and the above element, okay, 1, and same element 2, and copy the same row here again 3 0 0 3, okay. Now our adjoint of A is equal to, okay, find the determinant of this, okay. What is the determinant? We get 3 3s are 9, minus 1 into 0 0, we get 9, this is the element. And similarly find determinant of this, we get 0. Similarly find determinant of this, we get 3. Find the determinant of this, we get minus 1, minus 3 to the 6, we get minus 7. And find the determinant of this, okay, we get 3, minus 1, we get 2 here. And find the determinant of this, what is the determinant we get? We get minus 2, okay, minus 1, okay, minus 2 minus 1, we get minus 3, okay. find the determinant of this, we get 3 here. Find the determinant of this, 0. Find the determinant of this, we get 3. Okay, like this you should find adjoint of A. Okay, now we need to find determinant also, determinant of the A also. Okay, see, don't solve with normal method for 3 by 3 matrix. Okay, already you know adjoint of A. Okay, you know already adjoint of A and matrix we know. Okay, just multiply first row elements and first column elements here. Okay, first row elements in matrix A and first column elements in adjoint of A. Just multiply those two. 1 0 minus 1 and here 9 minus 7 3. Okay, just multiply these elements. 1 into 9 we get 9. Okay, 0 into minus 7 plus 0. Okay, minus 1 into 3 we get minus 3, we get 6. Okay, like this we get determinant of A. Then finally, what is adjoint A inverse? A inverse is equal to 1 by determinant of A into adjoint of A. 1 by determinant of A is 6, adjoint of A is 9 0 3 minus 7 2 minus 3 3 0 3. Okay, this is our A inverse. Okay, then we will discuss some important properties related to determinants. Okay, if you interchange rows or columns, that means if you swipe the rows or columns, sign changes. Okay, so for example, if you consider a matrix like this, A B C D E F G H I. Okay, for example, this is called row 1, this is row 2, row 3, you know. Okay, for example, if I will interchange in determinants, I am telling. Okay, not in matrices, I am telling in determinants. Okay, this property you should apply in determinants. See, if you interchange any rows or any two rows or any two columns, okay, you should take negative sign first outside, then interchange. Okay, like this. Okay, if you not take negative sign outside like this, your answer will get wrong. Okay, you should remember this one. This is the important property. Okay, if you apply row or column operation, you should remember this. And identical rows. Okay, identical rows or columns. Okay, determinant becomes 0. That means, for example, 1 2 3 6 7 8 1 2 3. See, first column and third column both are same, means identical. Okay, identical means same elements. Okay, both are same. Okay, both columns same, then we say that finally no need to expand this one. Okay, the direct determinant of this is equal to 0. Directly determinant of this matrix equal to 0. Okay, and triangular matrix, and you should remember this one, triangular matrix. If determinant is equal to product of diagonal ellipses, not only in triangular matrix, if the matrix is diagonal matrix, diagonal scalar, okay, identity, okay, triangular means it may be upper or lower triangular. Okay, determinant of A is equal to product of diagonal elements, product of diagonal elements. Okay, you should remember this one. For example, if the matrix is given like this, 8 0 3, okay, 0 1 2, okay, 0, okay, 0 minus 1. See, it is called as upper triangular matrix. Why? Because see, all the diagonals, it is the diagonal elements, main diagonal elements. Below the main diagonal elements should be 0. Okay, below the all the diagonals elements should be 0. There are all are zeros. Okay, then it is called as upper triangular matrix. Okay, it look like a triangular. Okay, it is called as upper triangular matrix. Then if it is upper triangular matrix, determinant of A is equal to product of diagonal elements. These are the diagonal elements, 8 into 1 into minus 1, that is equal to minus 8. Okay, it is same for diagonal, it is scalar identity or lower triangular also. Okay, you should remember. And this is an important property, determinant of Ka is equal to, if you take K outside, K power of n into determinant of A, K is any real number except 0. Okay, K should be any scalar value, that means any real number, okay, except 0, and n is equal to order of the matrix. Okay, n by n matrix, we know that. Okay, order of the matrix is very important property. And one more property, determinant of AB is equal to determinant of A into determinant of B. Okay, this is also one more important property. And determinant of A transpose is equal to determinant of A. This is also one more property, important one. Okay, determinant of adjoint of A, that is equal to determinant of A power of n minus 1. You should remember this property. See how to remember these properties. See, if you remember these properties, then you can solve any other properties easily. Okay, adjoint of A, determinant of adjoint of A. How to find determinant of adjoint of A? Determinant of A power of n minus 1. How to prove this one? Okay, see, remember this one. You know that A inverse is equal to 1 by determinant of A into adjoint of A. Okay, if you cross multiply this, we get adjoint of A is equal to determinant of A into A inverse. Okay, if you take determinant on both sides, get det of adjoint of A is equal to det of determinant of A into A inverse. Okay, that is equal to, we know that by the property, this property, determinant of AB is equal to determinant of A into B. By that property we take like this, determinant of A, okay, into determinant of A inverse. Okay, see, I already told det is just a number. Okay, it is a number, it is some constant value. From this property, okay, determinant of Ka, if you take any number, suppose any K value inside the determinant, if you take K outside, you should take K power of n. Okay, K power of n, like that. Det of A is just a number. If you take that number outside the determinant, we take determinant of A power of n. And also, what is the determinant of A inverse? Determinant of A inverse is nothing but 1 by determinant of A. Okay, that by that property we get 1 by determinant of A. If you take this into numerator, we get determinant of A power of n into determinant of A power of minus 1. If the bases are same, power should be added. Okay, we know that by the property A power of m into A power of n, that is equal to A power of m plus n. Same property, if the bases same, power should be added, like that. If the bases same, powers added, we get n minus 1, like that. Okay, like this, like that we get this formula. Okay, this is a proof of that formula, you should remember. Okay, there is a one more property, determinant of A power of R. Okay, R should be any integer. If you take that outside, we get determinant of A power of determinant of A whole power of R. The same property, this same property are applied. Determinant of A inverse, if you take minus outside, we get determinant of A whole inverse, like this. Okay, this property you should remember. And there is some other properties, determinant of adjoint of A. Okay, that is equal to same formula, determinant of A power n minus 1, but adjoint is repeated 2 times. Okay, for n minus 1 you take square. Okay, if determinant of adjoint of and so on, adjoint of A, if it is adjoint is repeated t times, okay, same formula, determinant of A power of n minus 1, but for n minus 1 take power t. Okay, like this you should remember these formulas. Okay, this is very helpful formulas, you can remember this one. And there is a one more property. Okay, we know that A inverse is equal to 1 by determinant of A into adjoint of A. Okay, just cross multiply, just swipe these two. Okay, interchange A inverse and determinant of A. We get determinant of A is equal to 1 by A inverse into adjoint of A. If you take A inverse into numerator, it gives us determinant of A is equal to A into adjoint of A. Okay, you should always remember this important property. You should always remember adjoint of A into adjoint of A, that is also always equal to determinant of A into identity. Okay, that is also written like this, adjoint of A into A. Okay, you should remember this very important property. A into adjoint of A, that should be equal to determinant of A into identity, that is also equal to adjoint of A into A. Okay, these are the very important properties you should remember. Okay, next, trace of the matrix. Okay, what is trace? Trace is equal to sum of diagonal elements. Sum of diagonal elements. Sum of diagonal elements. Okay, for example, if you consider a matrix like this, 1 2 3 6 7 8 9 10 11. Okay, the trace of the matrix, we denote the trace like this, trace of A. We denote with the symbol like this, trace of A. Okay, trace of A is equal to sum of diagonal elements. What are the diagonal elements here? These are the diagonal elements. Okay, sum of these elements. Okay, we get 18. Okay, this is the trace of the matrix. There are some important properties are there. Okay, for trace of the matrices, trace of A plus B is equal to trace of A plus trace of B. You should remember it may be plus or minus. Okay, if you get a plus, if you get minus, the property applicable. Okay, this is the very important formula. Okay, then trace of A, this is also equal to trace of A transpose. Okay, this is also important formula you should remember. Okay, and trace of identity matrix is always equal to n. Okay, n is equal to order of the matrix. Okay, and trace of any zero matrix always equal to 0 only. Okay, here O indicates that zero matrix. And there is one more property, trace of k times of A. K is any real number, you can take k outside, trace of A like this. Okay, these are the properties you can remember for trace enough. Okay, very important. Next, rank of the matrix. Okay, what is formal definition? Okay, we can define rank in two ways. Okay, one is row rank or column rank, the both are same. The maximum number of linearly independent row vectors. Okay, that is row rank. Okay, the maximum number of linearly independent column vectors are called as column rank. Okay, there is a theorem. Okay, the fundamental theorem of linear algebra says that for any matrix, okay, the row rank is always equal to the column rank. See, related to this key point, they asked one question in gate examination. Okay, that's why very important result it is. This theorem you should remember, fundamental theorem of linear algebra, rank of A, or sometimes we denote like this symbol also, rank of A. Okay, Okay, how to calculate rank of the matrix? The most common method to find the rank is using Gauss elimination. Okay, to transfer the matrix into row echelon form method. This is the there are various methods to calculate rank. Okay, there are major three methods. One is row reduced echelon form method. Okay, row reduced echelon form method. Second one is normal form method. Okay, third one is determinant method. Okay, determinant method is applicable for only square matrices. Okay, but row reduced echelon form method and normal form method you can apply for any order of the matrix. Okay, you should remember this point, very important. Okay, then okay, next and also there is a rule. Okay, rank of the matrix is equal to the number of non-zero rows. Okay, in its row echelon form method. In a row reduced echelon form method, rank of the matrix that is equal to number of non-zero rows. Okay, if number of non-zero rows equal to rank of the matrix. Okay, you should remember. Okay, for example, if you consider one example like this, you need to apply row operation. See, if you are applying row reduced echelon form method. Okay, row reduced echelon form method, you should apply only row operations. Okay, only row operations allowed. Okay, we not use column operations. Okay, but see, in normal form method we use both row operations and column operations. You can remember this one. In normal form method we use both row operations and column operations. Okay, I am not going to discuss normal form method, but I am going to discuss row reduced echelon form and determinant method. These are two are sufficient for gate examination. Okay, for your like exams. Okay, other than gate, is there any other exams? If you want, I can discuss in next videos. Okay, normal form method also. Okay, see how to apply row reduced echelon form. Okay, you should remember this rule always. Okay, the leading coefficient. Okay, the leading element should be always 1. Make leading element. The first step is make. Okay, make, or this should be 1. Okay, it is already 1, no problem. Otherwise, make leading element should be 1. Okay, it is 1. Then apply row operations. Make this positions and this position 0 first. Okay, apply row operations, make this position and this position is zeros. Okay, then after that, by using second row, okay, make remaining these elements, try to make these elements zeros. Okay, try to make these elements zeros again. See, the first step is you completed. Okay, if you observe that in this operation, by applying the operations, this become a 0, all the elements become 0. Okay, this is easy. Then you can swipe the rows and columns, sorry, row 2 and row 3. Okay, you can interchange like that. You get like again, and divide with r2 by -2, you divide like this. Okay, 1 2 3, we get 0 1 1 0 0 0. See, this position is already 0, this position is already 0. See, by using this one, if suppose if I will use row 1 to make this position position is 0, okay, if I will make this position is 0, then again these elements should like again these elements should be comes here, okay. There is no there is no changes, okay, there is no meaning in that, okay. The same thing we get again, okay. That means again the both are non-zero rows only, non-zero rows only, okay. There is no changes. Then here number of non-zero rows is a one row and this is the second row, and there are two non-zero rows, the rank of the matrix equal to 2, okay. And these are the some important properties you should know, okay. What are the properties? The first property, rank of A is always less than or equal to minimum of rows and columns, okay. And rank of AB is less than or equal to minimum of rank of A comma rank of B. And elementary operations do not change rank, okay. If you apply any operations, any number of operations, that does not change the rank of that matrix, okay. If you apply operations, row operations, okay, rank does not change, okay. If rank of A is equal to n, then rank of adjoint of A is equal to n. If rank of A is equal to n minus 1, then rank of adjoint of A is equal to 1. If rank of A is less than n minus 1, then rank of adjoint of A is equal to 0. And rank of A is equal to rank of A transpose. This is also important. If the matrix is square matrix, okay, if the matrix is square matrix, okay, square matrix means n by n order, okay. If determinant, find the determinants. If determinant of A is equal to 0, rank of A is less than n, okay. If determinant of A is not equal to 0, then determinant of A is equal to n. See, for example, if I will consider a matrix 3 by 3 matrix, like, okay, this is a 3 by 3 matrix. For example, if I will find the determinant of this, if I will get determinant equal to 0, if I will get determinant of equal to 0, then rank of this matrix should be less than 3, okay, should be less than 3, okay, you should remember. And rank of A never be 0, okay. Rank of the matrix never be 0. It may be, see, what is the order of this matrix? 3. Then the possible ranks should be 1, 2 or 3 only, okay. You should remember, okay. If determinant of A is equal to 0, then it is not, that is not equal to order of the matrix 3, okay. Now we need to check rank of that matrix is maybe 1 or 2. How to check it is 1 or 2? You should find again determinant of these submatrices 1 A B D E. Find the determinant of this, find the determinant of these matrices, okay. Any of these two matrices if not equal to 0, then order rank of that matrix equal to, this is 2 by 2 order, then that is equal to 2, okay. If both determinants equal to 0, then order of that matrix equal to 1 finally, okay. Both equal to zeros, then rank of that matrix equal to 1. If any of these is not equal to 0, then order should be equal to this 2 by 2 determinant, okay. If determinant of A is not equal to 0, then rank of A is equal to order of the matrix. You should remember this one, okay. Then system of equations, okay. There are various methods to check the system of equations, okay. Okay, this is the system Ax equal to B. A is a coefficient matrix, okay. B is right side, okay, right side elements, okay. X can be taken as variables, okay. Column wise you should take the variables, okay, given in the system, okay. There are two cases, okay. You should find the determinant, Okay, if determinant is not equal to 0, okay, there is unique solution. Unique solution means single solution. Okay, single solution means there is only x, y, z values. Single x, y, z values we get. Okay, if determinant of a is equal to 0, again there are two cases in this. Okay, no solution and infinitely many solution. Okay, no solution, infinitely many solution. For no solution, you should check adjoint of a into b. If it is not equal to 0, that is no solution. If adjoint of a into b that is equal to 0, that is infinitely many solutions. Okay, this is the one condition. And if solution will exist, okay, unique solution, if solution exists, that is nothing but consistent. We call as this is consistent. Okay, infinite solution, this is also consistent. If solution does not exist, that means no solution, it is called as inconsistent. Inconsistent, you should remember. Okay, here in this case b is not equal to 0. B is not a zero matrix, it is non-homogeneous case. Non-homogeneous case. Okay, the same pattern we apply for homogeneous also. Okay, but in homogeneous the thing is there are only two cases. Determinant of a is not equal to 0, unique solution. Okay, that is nothing but trivial solution or zero solution we call. If determinant of a is equal to 0, that is called as non-trivial solution. It is also called as infinite solution in case of homogeneous system. That means b is equal to 0, we get ax equal to 0. In homogeneous system of equations, there are two cases. Determinant of a should not be equal to 0, that is trivial solution. If determinant of a is equal to 0, that is non-trivial solution. It is also called as infinite solution. Okay, and there is one more method, rank method. You can apply if you want. You can apply rank method also. Okay, if rank of a is equal to rank of argumented matrix, that is equal to, okay, number of variables. Here n is nothing but number of variables. Okay, then it is a unique solution. If rank of a is equal to rank of argumented matrix, but it is less than number of variables, then it is infinitely many solutions. If rank of a is not equal to rank of argumented matrix, that is nothing but no solution. Okay, these are the two important points. This is the important thing for rank method. Okay, you should remember this one, rank method. See, I'm going to tell one shortcut trick. You should remember this enough. Okay, you should remember. If I will consider a system, okay, I will write a matrix A, B, C, D. If I will consider x is equal to some x, y. Okay, B matrix is C1. I will consider some different K1, K2 for example. Okay, it can be written as Ax equal to B, right? Okay, first, okay, this is the, remember this one. Okay, first find the determinant of A. Determinant of A is not equal to 0, unique solution. Okay, if determinant of A is equal to 0, there are two cases, you know. Okay, no solution, infinitely many solution. Okay, again, see, you get a system like this. Actually, if you write argumented matrix, okay, if you write argumented matrix like this, A, B, C, D, okay, K1, K2, you write argumented matrix like this. Okay, if you find determinant of A is not equal to 0, unique solution. If determinant of A is equal to 0, there are two cases. Again, no solution, infinitely many solution. Okay, again, what you should do, find the determinant of these elements B, D, K1, K2. The same trick for 3 by 3 matrix also. Okay, you should remember. Okay, if you find determinant of this, if you get this is equal to 0, this is infinitely many solution. If it is not equal to 0, it is no solution. That's simple. Okay, just remember this trick enough. Okay, if it is homogeneous, we not get no solution case. Okay, because in homogeneous solution is always exists, it may be in Q or infinitely many solution. Okay, that's enough, you should remember this one. Okay, okay, we will do some questions, okay, from 2025, from previous years questions. Okay, this is a question. Consider the matrix A. Which of the following combinations of alpha, beta or gamma is the rank of A is at least 3? Okay, what is the combinations of alpha, beta, gamma? The rank of the matrix A is at least 3. Okay, that means we should find alpha, beta, gamma values. Okay, we get rank of the matrix should be equal to 3. See, if you want rank of the matrix equal to 3, compulsory, see, these all elements should be zeros, then gamma also becomes 0. If gamma becomes 0, we get 3 non-zero rows. Okay, then rank of A is equal to 3. Rank of that matrix equal to number of non-zero rows, right? We apply the same concept here. Gamma should be equal to 0. Here gamma is not equal to 0 given, eliminate 1. Here equal to 0 is there, here not equal to 0 is given, eliminate this one. Answer should be this or this. Okay, see, if alpha also becomes 0, beta also becomes 0, gamma also becomes 0, we get rank is equal to 2, because this is also completely 0, this row also completely 0, then rank becomes equal to 2. Then compulsory alpha, any one of these should be not equal to 0. This is not equal to 0 or beta is not equal to 0. This should be compulsory. Okay, then alpha is not equal to 0. Yes, beta is equal to 0, gamma is 0. Only third one is the correct one. Okay, but in option, which one is the given? Okay, we will examine other way also. Wait. Okay, this is the true statement. Anyway, third one is a true statement. Okay, we will examine the first one also. If alpha is 0, okay, beta gamma is not equal to 0, then rank becomes 4, then we can eliminate this one. Okay, then not D option. Okay, okay, because third one is correct one, third one is correct. Okay, it is not equal to 0, this is becomes zeros, we get rank 3. Third one is correct, but is only 2 is given, we can eliminate this one. Here also only 4 is given, we can eliminate, there is only one option. Okay, only 1, 3 and 4. How is 1? Wait, we'll discuss. Alpha is 0, beta is not equal to 0, this is also not equal to 0. One minute, we will discuss with another way. We can apply determinant method. Then is a square matrix. It is a square matrix, we can apply determinant method. Gamma should be 0. Okay, if you consider the first statement, alpha is equal to 0, beta equal to gamma is not equal to 0. Okay, if you consider the matrix becomes like this: 2, 3, 4, 5, 0, 6, 7, 8, 0, 0, alpha also 0, beta may be any number, 0 0 0, gamma may be any number. Okay, then in this case we get rank of the matrix. Rank of the matrix is equal to 4. Okay, but we need at least, okay, at least, okay, at least, right? That means rank of a at least 3 means greater than equal to 3. Okay, it may be 3 or it may be, what is the meaning of this at least 3 means? It may be 3 or 4. Okay, yes, then it is a correct one. It is a true statement. We can take that one. If alpha 0, beta 0, gamma 0, we get rank of a is equal to 2, which does not satisfy this condition. Then we can eliminate this second one, false. Okay, then if you observe the options, here only 4 is given, eliminate. Only 2 is given, eliminate. Okay, what about third one? Third one, if you consider alpha gamma equal to 0, okay, these both become 0, this is non-zero. In this case also we get 3. Okay, then it is also a true statement. Okay, what about this? If all the cases alpha, beta, gamma is not equal to 0, this is not equal to 0, that means we get rank 4. Yes, this is also true. That means A is the correct. Only 1, 3 and 4. At least, because they used the word at least. At least means rank of A should be greater than or equal to 3. Okay, rank of A should be greater than or equal to 3, less than order of the matrix. How much? 4. Okay, that means this, what is the meaning of this? It may be 3. The rank of this matrix may be 3, 4, because rank is always gives natural number only. Okay, natural numbers. That's why 3 or 4. There is only 2 possibilities, 3 or 4. A is the correct option for this question. Okay, next we discuss, this is the question. If V is a non-zero vector of dimension 3 by 3, okay, then matrix A is equal to V into V transpose. Okay, try to solve this one. What is the value we get? They asking to find what is the rank of this matrix. Okay, order of the matrix V order is given 3 by 1. Okay, that means, for example, if I will consider V as V1, 3 rows 1 column, V1, V2, V3. Generally I can consider like this. V transpose we get V1, V2, V3. Okay, if you multiply these two, V1, V2, V3, V1, V2, V3, if you multiply this, okay, we get V1 square, V1, V2, V1, V3, okay, V2, V1, V2 square, V2, V3, V3, V1, V3, V2, V3 square. Okay, actually if you observe this one, row 1, okay, row 1 can be written as V1 into V1, V2, V3. Okay, row 2, similarly row 2 can be written as V2 common, we get V1, V2, V3. Okay, similarly row 3, V3 common, we get V1, V2, V3. Okay, if you observe that every row, okay, is simply a scalar multiple of the same vector V transpose. Okay, V transpose is this one only, right? This is see V1 V transpose in row 1, V2 V transpose in row 2, okay, V3 V transpose in row 3. Okay, see, observe that in row 1 you can take V1 common, okay, we get like this. In row 2 we take V2 common, we get like this, V3 like this. Okay, this is nothing but every row is simply a scalar multiple of the same vector V transpose. Okay, what is the meaning of this? Okay, what is the meaning of this? Every row, okay, scalar multiple of scalar multiple of the same vector V transpose. Okay, this implies, okay, the meaning of this, what is the meaning of this? There is only one linearly independent row, one linearly independent row. There is only one linearly independent row, okay, in the entire matrix. Okay, in the entire matrix. Okay, if you apply the properties, matrix property, okay, rank of AB, that is less than or equal to minimum of rank of A comma rank of B. If you apply this property, what is rank of V? Okay, rank of V is a non-zero number, the rank we get 1. Okay, and the rank of V transpose also equal to 1, and the rank of V into V transpose, okay, is less than or equal to minimum of 1 comma 1, that is equal to 1. Okay, the rank of this equal to 1 only. Okay, you should remember this point, that's it. Okay, there is only one linearly independent row. Okay, that means one linearly independent row, that is equal to row rank, we call as that is row rank. Okay, row rank. Okay, that directly the rank of this V transpose equal to 1. Okay, you should remember this one. And this is a question: let A and R3 denote the set of real numbers and a three-dimensional vector space over it, respectively. The value of alpha for which the set of vectors does not form the basis of R3. Okay, does not form the basis. Then we find the det. If it is not form the basis, means it is not linearly independent. If it is not linearly independent, means determinant of A is equal to 0. Simply find determinant. Okay, what we get, this element can be taken as 2 minus 3 alpha, 3 minus 1 3, 1 minus 5 7. Okay, not linearly independent means it is linearly dependent. If it is linearly dependent means determinant of A is 0, because it is clearly mentioned it does not form a basis. If it is form a basis, it should be satisfy two conditions: linearly independent, the vector should be linearly independent. Second one is the vector spans. Okay, spanning of the vectors. Okay, you should remember that one. Just simply find the determinant of this. Okay, what is the determinant we get? Simply find determinant. If you expand this one, okay, what we get, 2 minus 7 plus 15. Okay, minus 3 times of minus plus 3, 21 minus 3, and plus alpha minus 15 plus 1. Okay, finally we get 16 plus 54 minus 14 alpha, that is equal to 0. Okay, if you simplify this, we get 70 minus 14 alpha equal to 0. 14 alpha is equal to 70. Alpha is equal to 70 by 14. Okay, then alpha is equal to 5. Okay, 5 is the answer. 5 is the answer for this question. Okay, this is a very simple question. Okay, just you should know the properties. Okay, and this is the question: consider the system of linear equation Ax equal to B where the system of equation is admits. Okay, 1 minus root 2, 3 minus 1 root 2 minus. See, if you observe that this matrix is not a square matrix, then you cannot apply determinant method here. Then you go with rank method. This is a matrix A. Okay, 1 minus root 2 3 minus 1 root 2 minus 3. Then apply the row operation by the row reduced echelon form method. Apply the row method here. Okay, what we get, R2 tends to, otherwise if you observe that, okay, R2 tends to R2 minus R1, okay, R2 plus R1. If you observe that, okay, if you apply this one operation, we get 0 here, 0 0. That means non-zero row equal to 1. Okay, this is equal to 1. The same thing, what is the argumented? If you write in argumented matrix, I will write argumented matrix here also 1 3. Okay, 1 3 we get here actually like this, 1 minus root 2 3 0 0, we get here 4. Okay, if you observe that, rank of the matrix equal to 1, but rank of argumented matrix equal to 2. They both are not same. Rank of A is not equal to rank of the argumented matrix. Okay, there is no solution. If both are not same, then they both are not same. Okay, this is the clear one. Next, this is the question. Let okay, this question is related to eigenvalue eigenvector. Okay, no problem. Let's say 4 by 4 matrix is given. M has 4 linearly independent eigenvectors. Statement 1. Statement 2 is given. M has 4 distinct eigenvalues, and M is non-singular or invertible. Okay, which one is the which of the following is correct answer regarding this 4 by 4 matrix? Okay, for 4 by 4 matrix, you should remember the first statement. M has 4 linearly independent eigenvectors. Okay, it is 4 linearly independent eigenvectors means it definitely diagonalizable. It definitely the matrix M is diagonalizable. Okay, if it is diagonalizable, we cannot say that the eigenvalues are distinct. Okay, eigenvalues are distinct. Okay, it may be different also. Okay, we cannot say that means s1 s2 s1 implies s2. No, we cannot say that. Okay, see, always remember, if matrix A is diagonalizable, okay, that does not imply eigenvalues are distinct. Okay, but ulta is true. Eigenvalues are distinct, definitely matrix A is diagonalizable. Diagonalizable means linearly independent vectors. Okay, this is a 4 by 4 matrix, then 4 linearly independent eigenvectors. Okay, then S1 does not imply S2, but S2 implies S1. This is true. Then B is the correct answer. B is the correct one. S2 implies S1. Okay, M is non-singular. Non-singular means determinant of M is not equal to 0. Okay, see, if determinant is not equal to 0, we cannot imply. See, S1, see, if it is M is linearly independent vectors, okay, we cannot imply that determinant of A should be not equal to 0, because diagonal matrix, in diagonalizable matrices, eigenvalue Eigenvalue may be 0 also. Eigenvalue may be 0. Okay, if it is 0, okay, determinant of A is equal to product of eigenvalues. Okay, if any one eigenvalue is 0, complete determinant will equal to 0. That's why S1 also does not implies S3. We cannot say like that. And S3 implies S2, no, because if this determinant is not equal to 0 means we cannot say that eigenvalues are distinct. Eigenvalues may be same also if determinant is not equal to 0. That's why the D option also wrong, D also wrong, C also wrong, only B is the correct one. Okay, this is the next question. Let A and B are real symmetric matrices of same order, same size means same order. Which of the following options are correct? Okay, the both are symmetric matrices. They're saying both are symmetric matrices. Okay, we know that what is symmetric matrix. If A is symmetric, A is equal to A transpose. If B is symmetric, B is also equal to B transpose. We know this. Okay, just analyze the options. What are the options are given? See, the first one, A transpose, first option, A transpose equal to A inverse is given. Okay, if you take inverse this side, you get A into A transpose equal to identity. This is nothing but A is orthogonal matrix. Okay, orthogonal matrix not necessarily symmetric. Okay, that's why you can eliminate this one. And AB is equal to BA. Okay, AB is equal to BA. AB is equal to BA. It is only true, it is only correct, it is only true if A and B, okay, both are, okay, commute with each other. Okay, but two symmetric matrices do not necessarily commute. Okay, two symmetric matrices do not necessarily commute. That's why we can eliminate B answer also. And A is equal to, okay, we will come to C option, but A is equal to A inverse. Okay, nothing but it is can be written as A square is equal to identity. This is nothing but involuntary matrix. It is a involuntary matrix. Involuntary matrix sometimes symmetric. Okay, but in general, okay, it is not a symmetric matrix. Okay, in general it is not a symmetric matrix, but involuntary matrix sometimes acts like a symmetric matrices also. Okay, but in general it is not a symmetric matrix. That's why we can eliminate D answer also. But C is always true. Okay, because it is a general property for transpose of the matrix. Okay, AB are any square matrices. Square matrix means symmetric or skew symmetric, also square matrices. Okay, it is always true. Okay, if you take transpose, always take ulta B transpose into A transpose. This is standard property of transpose of a matrix. Okay, that's why C is always correct. Okay, it may be symmetric matrix, it is applicable to this statement is true for any square matrix. Any square matrix. Okay, you should remember that one. And next, this is a question. Consider the system of linear equations. They are asking to find the values of A and B such that there exists a non-trivial null space and system admits infinite solution. Okay, when system admits infinite solution, first condition should be determinant of A is equal to 0. Okay, find data of this 1 2 1 2 A 4 2 4 6 is equal to 0. Okay, expand this one, we get 6A minus 16 minus 2 we get 12 minus 8 plus 1, we get 8 minus 2a equal to 0, we get 6a minus 16 minus 2, we get 4 plus 8 minus 2a equal to 0, 8 minus 8 get cancelled, and 6a minus 2a we get 4a minus 16 is equal to 0, 4a is equal to 16, a is equal to 4, a is equal to 4. Okay, it may be here also a is equal to 4 is there, here also a is equal to 4, we can eliminate a and c. Okay, now we check b. Okay, which one is the b? Okay, let's check. Then find determinant of these coefficients. Okay, if it is infinitely solution, this element's determinant also equal to 0. Expand this, we get 4b minus, okay, we get here 72. Okay, minus 1, if we expand this one, ab minus 48 plus 5, we get 6a minus 16 equal to 0. Simplify this, we get 8b minus 14, okay, minus a value is nothing but 4. I will replace here 4b plus 48 plus 4, okay, a is 4, 6 4s are 24 into 5, how much it is? 20, 10, 12, 120 minus, okay, and we need to simplify this. Okay, 5 into 16 also there, 5 into 16 it is 80, that is equal to 0. Now simplify all the values. Minus 144 plus 48 plus 120 minus 80, we get minus 56, and 8b, this is 4b, is equal to 0. 56 divided by 4, 4b is equal to 56, b is equal to 56 by 4, that is equal to 14. Then D is the correct answer. D is the correct option. Okay, then this is the question. Okay, they are asking to find rank of the matrix. See, if you observe that first row 1 and row 2 are identical, then I can apply row operation r3 times to r3 minus r1. I will apply row operation to second row also, r2 times to r2 minus r1. I will get 1 1 1, this is 0, minus 1 minus 1 minus 2 minus 1, then this is 0 0 0. If you observe that the number of non-zero rows here 2, okay, rank of A is equal to 2. C is the correct answer. Then this is the question. If the rank of 5 by 6 matrix is 4, matrix Q, rank of Q is equal to 4, then which of the following statement is correct? Okay, see, that's why like previously I given formal definition. Okay, formal definition of rank of the matrix. See, if Q has 4 linearly independent rows and 4 linearly independent rows, we know that if a rank, okay, row rank, okay, that is also equal to column rank. That is nothing but, okay, Q has same, okay, same number of same number of linearly independent rows and linearly independent columns. Okay, Q has same number of linearly independent rows, linearly independent columns. If rank of Q is equal to 4, that means it indicates that 4 linearly independent rows. If it is 4 linearly independent rows, this is also equal to 4 linearly independent columns. Okay, then option A is the correct one. Q has 4 linearly independent rows, 4 linearly independent columns. That is the correct option. Remaining all are wrong. Okay, and this is the question: the system of linear equations. Okay, here you apply, you can convert, you get 1 1 1 6 1 2 3 10 1 2 lambda mu. If it is infinitely many solution, then this is the A matrix. Okay, the complete one is argumented matrix. Okay, first data of this matrix, data of the matrix 1 1 1 1 2 3 1 2 lambda. Okay, you expand here, 2 lambda minus 6 minus 1, we get lambda minus 3 plus 1, we get 2 minus 2. Okay, if you expand this, this is equal to 0 actually. Okay, if you expand this one, we get 2 lambda minus 6 minus lambda plus 3 equal to 0. We get lambda minus 3 equal to 0, lambda equal to 3. Here lambda equal to 3 is there, here also there. Okay, you should eliminate this. Okay, if you want to say it is infinitely many solution, this determinants also equal to 0. 1 1 6 2 3 10 2 lambda mu. Okay, this determinant also should be equal to 0. In place of lambda, consider 3. You get something mu is equal to some, it is also equal to some value we get. Here not equal to symbol is, here not equal symbol is there. You can eliminate this one. Directly you select C option. C is the correct option. Okay, no need to expand and simplify. Okay, just observation, by observation you can eliminate option A directly. C is the correct one. Okay, okay, for the shortcut tricks, please go and revise once again. Okay, okay, here it is a non-trivial solution. If it is non-trivial solution, nothing but P should be equal to 0. Okay, if it is non-trivial solution, the system should be homogeneous. If it is homogeneous, P should be 0. Okay, remember, under this is the system of equation. Okay, we need to check whether the system is unique solution or infinitely unknown solution. What is argumented matrix? 1 2 3 2 3 4 3 4 5 4 5 6. First find the determinant of this. Okay, what is the determinant? We get 1 2 3 2 3 4 3 4 5. Find the, expand this determinant. 15 16 minus 2 10 4 is a 12 plus 3, we get 8 minus 3 is a 9. Expand this one, we get minus 1 minus 2, we get minus 2 3, we get minus 1 minus 1 plus 2 to the 4 minus 3 equal to 0. If it is equal to 0, it is not a unique solution. Okay, it is not a finite also. There are two cases, it may be infinite or no solution. Okay, again you should find the determinant of these elements. Okay, 2 3 4 3 4 5 4 5 6. Expanded determinant. Okay, if you get this determinant equal to 0, it is infinite. It is not equal to 0, it is no solution. Expand this, we get 24 minus 25. Okay, minus 3. Expand this, 18. This is 20 plus 4 15 minus 16. This is 2 minus 1 minus 3, we get minus 2 plus 4, we get minus 1, we get minus 2 minus minus plus 3 to the 6 minus 4, it is equal to 0. It is equal to 0 means it is infinitely many solution. It is infinitely many solution. And the determinant of the matrix. Okay, how many rows? 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 4 by 4 matrix. It is 4 by 4 matrix. Okay, if you observe this, the clearly if you observe that diagonal should be any real number, the elements is present here, the same elements present here, that is, this is the symmetric matrix of this. See, I plus a cube can be written as I plus a into I plus a into I plus a. Okay, first simplify these two. Okay, what is the value we get? I into I square plus, okay, plus IA plus AI plus A square. Okay, this can be multiplied with IA, that is equal to I square is I only. Okay, if you multiply any matrix with identity matrix, we get same matrix. That means here A 2A we get, here A square nothing but here A. Okay, nothing but finally we get 3A. Okay, I plus A. Okay, multiply again these two, we get I into I square plus IA plus 3A I. Okay, plus 3A square. If you simplify this, we get identity plus here A we get here A square, in place of A square replace A, we get 3A here, we get 3A here A 6 7A we get. Okay, that is minus A. Substitute here in place of this, substitute I. Okay, in place of I minus A, if you substitute 7A get cancelled, finally we get identity matrix. Okay, finally we get identity matrix is the correct answer. Okay, okay, this is the things we covered. Okay, in next video I'm going to cover all this one, and also like we did a great job today, and we covered all the foundation of linear algebra. Okay, like matrix definition and all the basics related to matrices and special matrices, determinants, rank, system of equations. Okay, in the next video we will discuss eigenvalues and eigenvectors, okay, which is the highest weightage topic in linear algebra. Okay, I will give this PDF notes from the description. Okay, if this video helped you, like it and share it with your GATE preparation groups or GATE preparation friends. Okay,